So this video is going to be on continuity, and then we're going to do some review for the unit test. So the learning goal is learning how to tell where a function is discontinuous and how to test whether or not a piecewise function is continuous at a specific value of x. So continuity is something that will be very important in first year university, and you'll go through how to write a mathematical proof about it. In grade 12, we just more want to understand what it means to be continuous from a calculus standpoint. So it has to pass this kind of three-part test here. So for a function f to be continuous at a certain value of x, first of all, it has to be defined at that value of x. So it can't have no value, all right? So it has to exist. F at a has to exist. The limit also has to exist. So the limit as x approaches a has to exist, which means the limit from the left and the limit from the right have to be equal and equal some number L. And then the last part of the test basically says that these two things have to be the same. So the value that the function is defined at has to be the same as the limit, okay? And that's our three-part test to decide whether something's continuous or not. So I illustrated a little example here so we could compare the same function, and it's said that this function is continuous at x equals a, but discontinuous at x equals b. So we're going to apply our three-part test here and see which part or parts fail here. So at x equals a, so here's x equals a. First thing we have to check about at x equals a, here's our function, this curve here. And then also this little point up here. That's our function, passes the vertical line test. For every x value, there's just one y value. So f at a, first of all, it has to exist. So what is the value of f at a? If you look down here and over, it looks like it's L. Okay, so pass part one of the test. Second part, the limit as x approaches a of f at x has to exist. So then we're looking at approaching a from the left and approaching a from the right. And what's the curve doing? In both cases, it's approaching L. So that means the limit exists and is equal to L. The third part of the test says that these things have to be the same. So f at a and the limit as x approaches a of the function have to be the same. They are. So we can say, therefore, the function is continuous at x equals a. So now we're going to talk about x equals b. First of all, we want to know f at b has to exist. So here's b, f at b, so this hole should be right underneath b here. And but the point that's actually on the curve is at capital B, so f at b is capital B. Second part of the test, the limit as x approaches b in this case of f at x has to exist. So we've got the limit from the left and the limit from the right, both approaching L. So the limit does exist. And the third part of the test is that these two things are the same, but they're not the same. So we can say since b doesn't equal L, therefore the function is discontinuous at x equals little b. Okay, so there's our three-part test, and that's how you decide whether a function is continuous or discontinuous at a given value. So a function that is not continuous has some type of break in the graph. The break could be the result of a hole, a jump, or a vertical asymptote. So these ideas can lead us to some great generalizations. First of all polynomial functions are continuous over all real numbers. So if you remember from advanced functions and you were drawing polynomial functions, they would look something like this, smooth curve everywhere, defined over all real numbers, okay, continuous everywhere. So all polynomial functions are continuous everywhere over all real numbers. Also from advanced functions, if you remember rational functions, sketching them, they would have like maybe couple of broken up into pieces almost. Weird looking. That's an example of one type of rational function. So rational functions, they're continuous everywhere, so over all real numbers, except places where the denominator is equal to 0. Okay, so our denominator is g at x here. The places where the denominator is equal to 0, you're discontinuous. So you have either an asymptote like in the sketch I did, or you could have a hole in the graph as well. And saying it's continuous everywhere except where the denominator is 0 is the same thing as saying that rational functions are discontinuous at the zeros of the denominator. And then, so for piecewise functions, we want to check and see, are the two one-sided limits, so the limit from the left and the limit from the right, equal or not equal? If they're not equal, the function is discontinuous at the point we're talking about. So now we're going to try to use that test. So test the continuity of each of the following functions, but we just want to know, is it continuous or discontinuous at x equals 2? So the first function, f at x is x cubed minus x. We want to recognize that as a polynomial function, and we know from our generalizations that polynomial functions are continuous everywhere. So continuous everywhere, definitely going to be continuous at x equals 2. Okay, next one is a rational function. We know rational functions are continuous everywhere except at zeros of the denominators. So in this case, the denominator is going to equal 0 when x equals 2, which means that this one's going to be discontinuous at x equals 2. Still using our generalizations. The next one is a piecewise function. It's piecewise defined because we have this bracket here. And it says that it's always equal to x squared minus x minus 2 over x minus 2 when x is not 2. Okay, and we can see why would they have that restriction? Well, because if x was 2, the denominator would be 0. And when x is 2, the value is 3. So basically this guy right here says that h at 2 is equal to 3. Okay, so we know 1, 2, 1, 2, 3, we've got a point there. And then we'll look up here to draw the rest of it. Okay, so that looks difficult to draw, so we would hope that we could reduce this to something that was easier to draw a sketch of. And you can factor the numerator, it's a simple trinomial. And then these can divide out as long as x isn't 2, which is our restriction. So we can replace this with x plus 1. Okay, as long as this restriction x isn't 2 is in play. So what does y equals x plus 1 or h at x equals x plus 1 look like? It's a line with a y-intercept of 1 and also a slope of 1. Except x can't equal 2, so there would be a hole here, but it's already been filled in because we know in our second statement that h at 2 is 3. So 2, 3 would be right on that line. So it turns out it's a completed line if you draw it. Sorry, it should be straight without any gaps. So are we continuous at x equals 2? Yes. We've got h at 2 defined to be 3. The limit as x approaches 2 of h at x. So as we approach 2 from the left and from the right, our curve is approaching 3 both times. These are equal. They're both 3. So therefore, h at x is continuous at x equals 2. Another one here then. F at x is equal to, it's a piecewise function again, so 4 minus x squared when x is less than 2, and 0 when x is greater than or equal to 2. So if we do the greater than or equal to part first, we've got like f at, so 2 is allowed, f at 3 is 0, greater than 2, f at 4 is 0, so 1, 2, 0, 0, 0. So we can draw this piece of the function in. Now we'll draw the top piece here. So we're not really allowed to put 2 in. There would be a hole there. So I say we're putting f at a 2, these quotation marks there. 4 minus 2 squared is 0. So that means at 2, 0, there would be a hole. But again, that hole's already been filled in by the second piece. But then we can put anything less than 2 in. So f at 1, 4 minus 1 squared, which is 3. F at 2, 4 minus 2 squared, which is 0. Sorry, my bad, that should be 0. 4 minus 0 squared, which is 4. Then, so we've got 2, 1, 0, negative 1 now. F at negative 1 is 4 minus negative 1 squared, which is 3 again. F at negative 2, 4 minus negative 2 squared. So that's 0 again. F at negative 3, 4 minus negative 3 squared, should be negative 5. And we can draw in the second part of our piecewise function. We can see that that hole we put around a filled in dot so that it's continuous everywhere. But we could still check our test. So f at 2 is equal to 0. The limit as x approaches 2 of f at x, so the limit from the left and the limit from the right are both 0. These are the same. So therefore f at x is continuous at x equals 2. And again, no gap, no hole when we put the pieces together. So now we're going to start the review portion. So we're going to start off by evaluating some limits. This one, we've got this cube root of x here, so we're going to use substitution or change of variable. So we're going to let u equal the cube root of x. So if we cubed both sides, we'll get u cubed equals x. And as x approaches negative 125, u will approach the third root of negative 125. And that would, the third root of negative 125 is negative 5. So now we can change over the limit so it's completely in terms of u. So it's going to be u plus 5, and x is u cubed plus 125. So we have a sum of cubes in the denominator that's factorable. Make sure that you have the sum and difference of cubes formulas memorized for the test. So u cubed plus 25 is going to factor to give us u plus 5 times u squared minus 5u plus 25. And the u plus 5's divide out. So we're left with the limit as u approaches negative 5 of 2 over u squared minus 5u plus 25. Safe to let u approach negative 5 now. So negative 5 squared is going to be 25 minus 5 times negative 5. So we're going to end up getting 2 over 75. All right, so that one was done using a change of variable. The next one looks complicated as well. But if you recognize that the numerator is actually a difference of squares, so it's something squared minus something else squared, which factors to give us this pattern here. So if we follow that, that's a difference of squares, even though it's a complicated looking difference of squares. You can say what's being squared here is x plus 5b. So follow that pattern, it goes in the front of each bracket, a minus in one, a plus in the other, here and here. And then what's being squared here would be 4b over x plus 9b. The other different thing, we've got x approaching negative 9b instead of just a plain number, but you can see if you put negative 9b in for x, the bottom would be 0, so you can't just substitute. We've got some like terms here, so that's going to just end up being x plus b, and here x plus 9b over x plus 9b, so that's what we wanted to have happen, so that these divide out. So now it's safe to let x approach negative 9b. And we end up with the limit being negative 8b. So that one was, the algebra wasn't quite as bad as a change of variable question or a sum or difference of cubes, but it was different because the limit was approaching negative 9b in terms of a variable, not just a number. And we had to see that, notice that difference of squares pattern to be able to factor it efficiently. Okay, now we're going to review slope of the tangent at a point. So we're going to find the slope of the tangent to this curve, y equals 2 over 3 minus 4x at the point 1, negative 2, using the first principles formula. So let's just write out what that was first of all. So it was m tangent, it was a formula, so it had started with equals the limit as h approaches 0 of f at a plus h minus f at a over h. Okay, and in our case, a is 1. So we can say the limit as h approaches 0 of f at 1 plus h minus f at 1 over h. So then we would need to find out what is f at 1 plus h. So that's going to be 2 over 3 minus 4 times 1 plus h. So 2 over 3 minus 4h if you distribute the negative 4, or 2 over negative 1 minus 4h. So go back to this side. And we can replace f at 1 plus h with 2 over negative 1 minus 4h. And then we're subtracting f at 1. So this is f at 1, negative 2 up here. So minus negative 2, but we would want to change that to plus 2. Over, don't forget that over h there. That's why we can't let h approach 0 right now, because of our problematic h in the denominator. So now we have a fraction and a whole number that we're adding, so we're going to get a common denominator within the numerator. This numerator can stay the same because we didn't alter the denominator. Here we have to multiply the numerator by negative 1 minus 4h, still all over h. So next, we're going to add the numerators over the common denominator in the numerator. Expand here, so 2 minus 8h over negative 1 minus 4h, and then we can do this divide by h by multiplying by 1 over h. So 2 minus 2 is 0, so we're left with negative 8h on the top. And in the bottom, we'll leave it in unfactored form. So here's my monomial times my binomial. And finally, we're able to divide out this problematic h so that it would be safe to let h approach 0. And as we do, we're going to have negative 8 over negative 1, giving me 8. So therefore, the slope of the tangent is equal to 8. Just make sure that's what they asked for. Find the slope of the tangent to the curve y equals 2 over 3 minus 4x at the point 1, negative 2 using first principles. So that's what we did. So we can box up our answer and try the next one. Okay, next type of question. If f at x is the square root of 2x minus 7, then find a f prime at x and explain its meaning. B, find f prime at 8 and explain its meaning. C, determine the equation of the tangent line to the curve y equals f at x at the point 16, 5. Okay, so first to do A here, we want to find f prime at x and just explain what it is. So it's going to end up being a formula that helps us find the slope of the tangent anywhere to that curve. And the formula for f prime at x is it's the limit as h approaches 0 of f at x plus h minus f at x over h. So we have to figure out what f at x plus h is so we can substitute in. So I'm going to do that over here. So it's going to be the square root of 2 times x plus h minus 7, or the root of 2x plus 2h minus 7. So then we can substitute in here the limit as h approaches 0 of square root of 2x plus 2h minus 7 minus f at x, which was defined to be the square root of 2x minus 7 all over h. So that one's definitely going to be, limit's going to be evaluated using multiplying top and bottom by the conjugate of the numerator. So 2x plus 2h minus 7 plus square root of 2x minus 7 over the exact same thing. So we're really just multiplying by 1. Then we're going to do FOIL in the numerator. So we know that that ends up being the first two multiplied together, which undoes the square root. The middle terms are going to cancel. A negative times a positive is a negative, but we're subtracting whatever happens to be under the root sign, not just whatever happens to come first. And then we'll write our denominator as our monomial term times this conjugate. Okay, so we're going to simplify in the numerator now. So actually I'll distribute first. So negative 1 times 2x is negative 2x, and negative 1 times negative 7 is positive 7 over h times this. Conjugate. Simplify by collecting like terms in the numerator. 2x minus 2x, negative 7 plus 7. So we're just left with 2h over h times this. The h's divide out. So now it's safe to let h approach 0. And when we do that, we're going to end up with 2 over the square root of 2x minus 7 plus the square root of 2x minus 7, or 2 over 2 root 2x minus 7, because there's 2 of them being added together. Then our 2's are going to divide out. So therefore, we figured out that f prime at x is equal to 1 over the square root of 2x minus 7. And what does that mean? f prime at x is a formula to find the slope of the tangent to the curve at any value of x. Okay, so that's what the derivative means. So that's A, we've done that. Part B says find f prime at 8, and also to explain its meaning. So f prime at 8, we're going to use our formula for f prime at x. Just replace x with 8. So that's going to be 1 over the square root of 16 minus 7, 9, which is going to be a third. So what does that mean? Therefore, the slope of the tangent to the curve f at x equals root 2x minus 7 is 1/3. So the slope is 1/3 at the point where x equals 8. So f prime at 8 is a third, which means that the slope of the tangent to the curve f at x equals the square root of 2x minus 7 is 1/3 at the point where x equals 8. And then C, determine the equation of the tangent line to that curve at the point 16, 5. So that's going to be where x is 16. So we'll substitute into our derivative formula again. So it's going to be 2 times 16 minus 7, 1 over square root of 25, or 1/5. So that's our slope. So therefore, m tangent is equal to 1/5. We know a point, 16, 5. So far we know y equals 1/5 x plus b, but we know the point 16, 5 is on the tangent line because it's the point we're finding the tangent at. So we can replace y with 5 and x with 16. Find b. Multiply everything by 5. So 25 minus 16 is 9. So therefore b is 9/5. So therefore equation of tangent line is y equals 1/5 x plus 9/5. You could have also done it using the scalar equation if they asked for it in standard form. You could have converted the slope to a normal. And the normal would be, so it's delta y over delta x, 5, first to direction vector. So 5, 1, which means our normal would be 1, negative 5. And then you could have done qp dot n equals 0 if you wanted as well. And then you would have had the equation in standard form. If it doesn't specify, it's whatever you prefer. Okay, so we did that, determine the equation of the tangent line. Next question is an application question. So a medicine is administered to a patient. The amount m of the medicine in milligrams in 1 milliliter of the patient's blood t hours after injection is given by that formula, and it's only valid for 0 to 3 hours. So find the average rate of change over the first 2 hours. So again, we talked about that meaning from time equals 0 to time equals 2 hours. And average rate we know, so we can just use m for like slope average is equal to, so it's going to be capital M at 2 minus capital M, is our function's title, at 0 over 2 minus 0. So M at 2 is 2 minus 1/3 times 2 squared, which is 2 minus 4/3, which is 6/3 minus 4/3, which is 2/3. M at 0, they both involve t, so it's just going to be 0 over 2. So it's going to be 2/3 divided by 2, which is 1/3. And then we want units. So our top is measured in the amount of medicine in milligrams, and the bottom is measured in hours. So the average rate of change is 1/3 of a milligram per hour. So therefore, average rate over first 2 hours is 1/3 of a milligram per hour. Instantaneous rate of change at t equals 2 hours. So now we're involved in calculus. So instantaneous rate, M instantaneous, is going to be the limit as h approaches 0 of capital M at 2 plus h minus capital M at 2 over h. So the limit as h approaches 0 of M at 2 plus h. So we got to figure that out. So M at 2 plus h is equal to 2 plus h minus 1/3 times 2 plus h squared, which is 2 plus h minus 1/3 times 4 plus 4h plus h squared, which is 2 plus h minus 4/3 minus 4/3 h minus 1/3 h squared, which is, okay, so collect 2 minus 4/3, so 2 is the same as 6/3 minus 4/3, which is 2/3. So plus h minus 4/3 h, so that's like 3/3 h, minus 4/3 h is minus 1/3 h. So I've used up that, minus 1/3 h squared. So we can replace capital M at 2 plus h with 2/3 minus 1/3 h minus 1/3 h squared, and then this minus M at 2, which we figured out was 2/3 from the question before, all over h. So we have 2/3 minus 2/3. We can factor an h out, and we get negative 1/3 minus 1/3 h over h. And then our h's divide out, so we can let h approach 0, and we get negative 1/3. And that would be milligrams per hour again. So therefore, at 2 hours, the instantaneous rate of change is negative 1/3 milligrams per hour. So the amount in your bloodstream is decreasing by 1/3 of a milligram every hour at 2 hours, but over the first 2 hours, because it's going into your bloodstream, the average rate is positive 1/3 milligrams per hour. All right. So I just put together the success criteria, kind of things we went over today, but things that are important for this first unit. We can draw a piecewise function and discuss continuity. Know that all polynomial functions are continuous over all real numbers. Know that all rational functions are continuous except at the zeros of the denominator. Understand what it means for a function to be continuous at x equals a. We can evaluate limits. We can use the first principles formula to find the slope of a tangent at a specific point. We can use the derivative formula to find the formula for the slope of a tangent at any point on a given function. We know f prime at x means slope of the tangent at a general point, and f prime at a means slope of the tangent at the point where x is a. And we know the difference between average rate of change and instantaneous rate of change.